First, let's have a look at conventional segmentation. If we want to separate the signal from the background, we can go to our histogram and we can see that there are two distinct populations here. We can set the intensity threshold value around here where it looks like the separation will be okay. And this is the resulting thresholded image. You can also find the threshold using a negative control image or from the background area in the image itself. However, to be objective, you should really apply the same threshold to all images. However, many real images have different background levels, and the background level can change over time or even in the same sample in the case of live cell imaging. To correct for these situations, we can use the auto threshold algorithm to correct for each image individually. There are many algorithms available and some may work better than others depending on the image. In Fiji, if we want to test which algorithm works best, for example, we can test up to 17 auto threshold algorithms and automatically test 9 local methods. When we have found the best method, we can then apply the same auto threshold to each image. So here you can see that the triangle algorithm is clearly the best one for this image. Conventional thresholding works well with fluorescent images, but it doesn't work as well with bright field, phase contrast, or electron microscope images. For these type of images, we can use machine learning to do the segmentation. In this approach, the pixel segmentation is done by the users to annotate and categorize different pixel groups. The software will then analyze the image for different features, not just by intensity, but also by color, texture, and surrounding context, and then calculate the likelihood that each pixel will fall into one of these categories. Then it will create a probability map that we can convert into a binary image. These programs are often easy to use and don't require any programming. Examples can be found in Harmony, Fiji, and Elastic. A more advanced approach to image segmentation is deep learning. Deep learning modules can automatically extract relevant features from an image and can also detect complex patterns. For example, here, deep learning has been used to detect overlapping nuclei in an image. These techniques often use some manual annotation input by the user and then some additional computation to train the software to recognize the desired features. Some examples of deep learning tools are UNet and StarDist in Fiji, UNet in Cell Profiler, or Stringer in Cell Pose. Another type of image segmentation is template matching, which is a computational approach. It doesn't need any manual annotation, but it does need one or more template images. And it's very useful if you have a large number of images where you will see similar structures. And again, this will create a probability map, which will then provide some likely candidates that match the template. And it's good for looking at the same feature in multiple images, such as a time lapse or in tissue microarrays. Again, no programming is needed for this plugin, which is available in Fiji. After segmenting pixels and creating a binary image, we can do some other morphological operations. We can separate objects using something like a watershed tool. You can reduce an object down to a 1 pixel width structure, which is called a skeleton. You can erode objects by a single pixel or dilate them to increase their size by a pixel. You can also fill in holes where necessary or erode the binary image down to just a single point. And then there are other tools like the Euclidean distance map and Boolean logic that can also be applied. These tools are very common and they're available in most software packages.